Welcome, thanks for joining me. So today I'm going to talk a bit about Linux namespaces, mainly because I find them really fun. So I'm Martin. I work for Cisco here in Norway. I've been there for quite a few years now. All I do is very Linux based, and that's why I do stuff like very specific Linux stuff like namespaces. Before we begin with anything, just a warning. Never run any of the code from these slides. So the code I have on these slides needs to fit on one slide, which means there is no error checking. There's a lot of crap code, so if you try and run this and something happens, you won't know and you will think everything's working fine. Please check errors. It's not my fault if you do. That's on you. Anyway, let's talk about namespaces. And that was a bit in the way. Move it to the side. Yeah. So what is a namespace? And it's not like one of the ones on the left here, which you might be familiar with from languages like C++ and probably C# and stuff. I don't know C#, but it might have namespaces. It's something that wraps a global kernel resource. Kind of depends on what you call a resource. But Linux has a lot of different namespaces which can work by themselves or together. And they are heavily used in, for instance, sandboxes or in containerization. So Docker is a heavy user of namespaces. Some namespaces are pretty specific to the container use case. They are created in one of two ways, either by using the clone system call with some flags, or the unshare system call. So in these slides, we'll always use unshare because clone is a pain. And the main idea is to just create them and see how they work anyway. So I'm not going to take you through the pain of using clone. But we'll start with what I think is an essential namespace. First of all, what namespaces do we have? And these are just a quick list of them. I'll try to get through all of them, not in this order. Some of them I will go quite quickly through because I find them less interesting, or they're very specific, or something like that. But I'll try to spend some more time on the ones I find interesting, at least. And we'll start with the user namespace. So the user namespace isolates users and groups and manages permissions in a way. Basically, it manages permissions in other namespaces. So often you group namespaces in user namespace and non-user namespace. And one thing to note here is that when you boot up a Linux system, you're already using namespaces. Everything is in an initial namespace. There is no way to run Linux today without being in a namespace. So with the user namespace, you create it by using the clone new user. And the reason I start with it is because normally, I can't speak anymore. Normally, you need capsys admin privileges, which is basically root, to create a namespace. Except if you're in a user namespace. Because every non-user namespace is governed by a user namespace. So every other namespace is kind of owned by a user namespace, and the privileges are defined in the owning user namespace. So when you mess around with user namespaces, you get a hierarchy of some sort. So in this example, NS0 is the initial user namespace that you create. And in this example, you're user 1000 and group 1000. Then you create other namespaces where you suddenly get other users and group. And this file format here is actually the file format you use to do the mapping of users from a namespace to the initial namespace. So what this means, the first line is the first part here is the user mapping. And that says that user 100 inside of the new namespace should map to user 688 outside of it. And you do that for 500 IDs. So if you do the maths, and if I haven't done it wrong, then UID 1000 in the initial namespace here should map to UID 412 inside the new namespace. And inside the user namespace, you can create new user namespaces where you are some sort of root. But it's important to note that this doesn't give you extra file permissions, for instance. Even though you are root, and root in theory can do everything, you still can't open up files that your mapped user can't open. So even though you are UID 0, the permission checks for file system access, for instance, is done by the initial namespace. And oftentimes, like in NS2 here, where we map user 0 to group user 0 inside the namespace to user 1000 outside of it, and we only map one user, every file and directory and everything on the system that is not owned by UID 1000 is owned by nobody, because we don't know what that user is inside of the namespace. I'll show you how to actually write to these files and what these files are. So, to create a user namespace, all you have to do is add clone new user to your call to unshare. After this line, you have created a new user namespace and you have entered it. But currently you don't have any user because you haven't mapped anything. So that's the next step, is to map the user and the groups like we did before. And that's these two files, proc self UID map and proc self GID map. Those are the files you have to write to set up the mappings. And what I do here is before I enter the namespace, I fetch my effective user and group, and I map my effective user and group to UID and group ID 0. So after these files have been written, I should be user 0 and group 0. So before this, I will be nobody, because I don't have a mapping. And after this, I would expect to be 0, 0. Turns out I'm not, in most cases, because there are some rules governing these two files. So in unprivileged namespace, in unprivileged user namespace, like this is, I'm not running this as root, I don't have any permissions in the parent namespace, I'm only allowed to write a single line to these files. That line can only map a single user, and that user has to be the user that is writing to this file. So I'm only allowed to map myself, basically, if I don't have cap set UID. If I have set UID, I can do anything. Which is why, for instance, docker d is running as root, because then it can write whatever it wants to into these files. But the problem here is that this call to write fails. And as I'm not checking error codes, then I don't know that they fail, but it does fail. The reason is I'm unprivileged, so I'm not allowed to add myself to new groups, not allowed to change groups. And so before I create a mapping, I have to write deny to this proc self set groups file, which stops me from changing groups and does a lot of stuff. And when I write this, then the mapping write succeeds. And if I checked error codes, I would know that that's what's happening. So, to show you how it works, I have this script. So this one is basically the code that I showed you. So I start up, I print out who I am. So I'm user 1000 group 100, and the only capability I have is cap wake alarm. It's not even in my effective set. It's in my inherited set. So I create a new user namespace using the unshare call. And now you see I am, well, user in group 65K, which on this system is nobody. And I have all permissions. And that is because I own this namespace, this user namespace, and I have all capabilities in this namespace and for all the namespaces that this namespace governs. And I can change groups and users if I want to, which is the next thing I do. I write to these files and I then get user 10 and group 42. Because in this particular case, that's what I write. And I still have all permissions. And of course, depending on how you use it, you should drop the privileges that you don't need and all that stuff, but I'm not doing that here. So the user namespace is required so that you can manage other namespaces. Or you need permissions in the user namespace to manage the other namespaces. So next up is the mount namespace. And this is pretty flexible. So what it does, it gives you a new list of mount points. So in the original namespace, you have a list of mount points, which is everything that is been mounted in this namespace. And what it does, when you create a new mount namespace, is you copy that list of mount points, but that list is now yours. So you can mess around with it. So you could use this to completely rewrite the file system. You create it by, in addition to the clone new user, you add clone new NS. And you might think that that's a weird name. That's because it's clone new namespace, because this is the first namespace that was created. And when it was created, nobody thought they would ever make a new one. So shit sticks. Yeah, but you can also propagate changes that you do in your namespace to your previous namespace, or vice versa. So you have some propagation methods. You can say that it is that the mount points are shared, that they're private, that they're slave, or unbindable. So shared means that they are mirroring each other. So one change in either your previous or your new namespace will propagate to the other. Private means that they won't. So they are completely isolated sets. You can do whatever you want in one of them. Or when I say whatever you want, you can do whatever you want with the list of mount points. If you have the same mount point mounted in the two namespaces and you write files, that is visible because you haven't changed the contents of the mount point. So if you have the same mount point, everything you do inside of it will propagate. Or it won't even propagate, it will be the same. But you can do whatever you want with the list of mount points. MS slave will say that you are in the new namespace that you just created. All changes from the previous namespace will propagate to you, but all changes you do will be private. Or then you can do unbindable, which says that this mount point cannot be bind mounted anywhere else. So that's stuck to where it is right now. And this is not something that you need to do on the whole system or none of the system. You do this on a per mount basis if you want to. And when you create a new mount namespace, you should set your preferred propagation, because that might be unexpected depending on what your system is. At one point, we had sysv as the init system, and with sysv, it was private. The default was private. But then systemd came along and they changed that to shared. And if you don't really know exactly what you're running on, then you should definitely set it explicitly, because it might be different depending on what computer you're running on. So, strategy for making our own root file system, which is one of the more fun things you can do here. And that's basically what Docker does. It creates a new root file system for you, which looks like a Ubuntu or Debian or whatever you want it to look like. So, first step, create a new mount namespace. Second, make all the mounts private, because I don't want anything to be propagating. Then I want to build up a new rootfs structure. And then I want to swap to that. And thereby get rid of the old one. So, creating a new mount namespace, clone new NS. So we created and entered a new mount namespace in addition to the user namespace. And by doing it like this new user namespace will govern the new mount namespace. You are guaranteed that if you, in unshare or clone, add more flags for namespaces, where one of them is the user namespace will be created first and govern all the other namespaces that you create. That's a guarantee you get from the kernel. And this, the new mount namespace, is exactly the same as the old one. So next thing I do is I make everything private. So I go to the root of my current file system. I set the mount points private, and I do that recursively. So now I'm no longer no longer propagating changes between the two namespaces. So now I'm actually isolated and can do whatever I want with my list of mount points. And then I start creating stuff. So what I like to do in this case is to mount a tempfs on /temp. I use /temp because I know it's there, and it's probably not needed for this application, so I can mess around with it. And as I know, this change is not propagated, so I'm not messing up anyone else by mounting a new tempfs over temp. Then I create some directories, I bind mount some stuff. It's not really important what I bind mount in this case, because I'm just creating a new root file system, and what that will contain kind of depends on your use case. But since this is a mount point that only exists in my namespace, I can write files, I can make directories, I can make big structures of everything, and no one else will see them. So when I created my rootfs, the next thing is I need to swap my new rootfs to be my rootfs. And there's two choices here. This is one, and that is using the pivot root system call. The way that works is it takes what is supposed to be the new root file system, and it also takes a directory which is where it's supposed to put the old root file system, because pivot root will keep that. After running pivot root, I cd to my new root file system, because if not, I'm still wherever I was before that, which means I could be leaking information that way. So you should always cd to somewhere inside of your new root file system. And then I unmount the old root and delete it, because I don't actually want that pointer back, because if I had it, I could do pivot root to get back out again, which would break my isolation. The other way of doing this is to use chroot. The problem with that is that it's limiting, for instance, making new user namespaces. I want to keep that option open, so I use pivot root, which you have to implement yourself because it's not exposed to glibc. So you have to call that yourself using the syscall glibc function. But it's a small enough task. And it keeps all options open. So in Docker, you could actually have sub-Dockers, like inside of a Docker image. You could have Docker running other Docker images. And that's because pivot root allows that. Another use case of this which I actually implemented in our unit test framework at work, is you can use this and give your unit test its own view of the file system, which means you can actually mess around with the file system inside of your test and see that it behaves as expected without anyone else seeing that, which I find pretty cool. Okay. Another quite essential namespace is the PID namespace. So the PID namespace is there to isolate, well, process ID numbers and isolate processes. So the idea behind it is that it hides that you're running on a system with other processes. So in a Docker image, for instance, they use this so that you don't see that there are other processes running. Of course, there's lots of other processes running on a system running Docker, but the Docker image itself won't see them because of the PID namespace. It kind of starts counting process ID numbers again. So the first process inside of this PID namespace will be 1, which is important because the PID1 in Linux is special. It has a task. It is the init system. And despite its name, the init system's most important task is not to initialize new processes. It is to kill them, or to kill orphan processes. So if you have more than one process inside of a PID namespace, the first process has the job of the init system, which is why Docker recommends you to only have one process inside of a Docker image, because if not, PID1 needs to be an init system. This namespace is also pretty different because when you create it, when you do unshare clone new PID, you're only creating the new namespace and it's empty. You're not entering the new namespace. If you use clone, you will enter it. The reason for that is that a lot of processes don't really like getting their PID changed mid-run. And glibc, for instance, is caching your PID. So if you did this and you were put right in, then glibc had to change, and the Linux kernel wouldn't break user space, as they try to avoid. So the first child process of the process calling unshare clone new PID will be the first process in the new namespace. And kind of similar to the user namespace, there's a mapping from the process ID counts inside of your namespace to what it is outside. So in your parent PID namespace, you see the actual, or your view of the PID counting. So for instance, here in NS0, we have PID 1024. And if you follow the pointers down here, you see that PID 1024 in namespace 0 is PID 2 in namespace 2. And it's PID 1 in namespace 3. But the process itself is running in namespace 3, and it has no idea that its actual PID is 1024. It thinks it's 1. And PID 1 in namespace 2 thinks it's 2. So they only see their own view of the process IDs. Now, to create a new PID namespace, kind of do the same as we already done a few times now. You add clone new PID to your list of namespaces in unshare. And after this, you have created a new user, mount, and PID namespace, and you've entered the user and mount namespace, but not the PID namespace. Because after doing this, you need to create a child process, for instance, by using fork. And that puts the new child into that namespace. And in the parent, you would then typically just wait for the child process to die, which is what we do at the end here. Wait PID just waits for that PID to exit. So this new PID, this new process here, will be PID 1. Now, one effect of doing this together with the mount namespace is that now I can mount a new proc FS. Because the proc FS is owned by the PID namespace. So if I don't create a new PID namespace, I don't own the proc FS. I can't mount it because it's not governed by the user namespace that I created. And if I were to keep the old proc, then it would show all the processes actually running on the system, so that would be an information leakage. Let's see, I also forgot, I did not show you the mount part, but that can be done quite quickly. So this is all the folders that's in my root of my file system when I boot up. And I create a new rootfs, and I basically remove everything except user and bin. Not sure what I actually put in this. But after pressing enter, I've completely rewritten my file system. But for the PID-NS, so I see I have some PID, 12943. I create and fork off, so I have now a child process which gets PID 1 suddenly. And if I list the newly mounted procfs, the interesting part here is the end. I only have one numeric folder in /proc, which is my one process. If I do that in my initial namespace, I see quite a few more, because this is a running system. It has lots of software running. But inside of my PID namespace, I don't see these. So this makes it, or at least is, a big step in making it look like you're running solo on the system, that there's no other processes running, and that there's basically nothing to compromise on this system, because this is the only application running. So next up, we'll talk about the time namespace. What the time namespace allows you to do is to control the boot and the monotonic time, or the boot and monotonic clock. You create it by using clone new time. And along with the PID namespace, this is a special namespace in that unshare doesn't put you in it. But also, this is the only namespace that you have to create using unshare. Clone will not create this new namespace for you. The reason for that is that you are controlling the monotonic and boot clock. Meaning the way you do it is you write an offset into some files. That file can only be written to as long as there is no processes inside of the namespace. Because boot and monotonic clocks are supposed to go in one direction. They're supposed to monotonically increase. So if you start runtime messing around with those clocks, then the process might get into funny issues, especially if it actually expects the time to be monotonically increasing. So unshare will create a namespace, empty, and there's no way to create it and put something in it automatically. You have to explicitly put something in it. either by using fork, like with the PID namespace. Every child of this process will be put into the namespace. Or you can explicitly move yourself after creating it. But you need time to actually write the time offsets before anything enters it. When anything enters the namespace is locked. But why does this exist? Because this seems extremely narrow. You're only messing with the boot time and the monotonic time. Like you're not changing the system time, and it's very, very specific. The use case that this was created for is for container migration. I haven't found any other use cases for it. They might exist, but what you do when you migrate a container is you freeze it in place, you move it, and then you start it up again at the same point that it was, so you kind of want the clocks to behave as they should. So you want the timers to be increasing still, and hopefully start around the same time that they were previously. So that's the use case for it. So you create it by using clone new time, and then you have to set the time using this file. Now this PID is your own PID, so proc self time ns offsets, and this is the format of it. You have to write this file one line at a time with open and close. So open, write one line, close it. Open, write one line, close it. And this seems inefficient, but proc is not a real file system, so you're not actually writing to disk, you're just telling the kernel stuff. So the first argument, the first part of the line you write is what clock you're changing, the offset in seconds and the offset in nanoseconds. So you can write it like this. So my write here opens and writes and closes, and you write boot time, whatever offset you want in second and in nanoseconds, and the same for the monotonic time. This offset might be negative, because you can, before anything has entered it, move the time backwards. But you cannot move it past 0. You can't have a negative time. There are rules for what you can actually write as offsets here. You also can't move it past the size of, is it int64 or something? Or uint64? I'm not really sure. But you can't move it past some point either. You can't have too large an offset. But you can have pretty large offsets. And after this, you can put something into the namespace, and it will get whatever time you set it, plus whatever time has elapsed since you set it, of course. When you want to enter the namespace, you can either fork, like we did with PID, or you can use setns with this file, proc self ns time for children. That will put your current running process into this namespace. And of course, I assume that when you actually make this namespace and you explicitly do setns to this symlink, you do know what you're doing, and your process won't collapse because time has changed. If not, you're doing it wrong and should fork. The way to do that is you open a file handle to this proc self ns time for children, which is a symlink to the namespace, and then you run setns with whatever namespace you want to join to this file descriptor. So after this line, you are in the new namespace with the new time. Let's quickly show that, because that's a small and simple demo. Oh, where am I? Oh, shit. So when I start up now, this is my current clocks, and I can now created the new time namespace, but in the process that created it, nothing has changed, because I haven't done anything, I haven't entered it. But when I write to the file and fork off a child, it's suddenly not so long ago since it booted, and the monotonic clock has increased quite a lot. And then I can use the nsenter to join with the parent process as well. But like I said, this has a very specific use case, as has this. So, UTS namespace. The UTS namespace isolates your host name and domain name. Basically, you have your own separate host name and your own separate domain name that you can set freely. You create it and join it by clone new UTS. Which, together with the user namespace, gives you permission to set a host name and set a domain name. But this is, of course, the domain name and host name for this namespace, not for the rest of the system. So in Docker, you could set your own host name and your own domain name, and you can do routing and stuff like that based on whatever you set inside of Docker. And this is what it's using. So you add clone new UTS to unshare. And at that point, even though you're running as non-root and don't really have permissions, you can suddenly set your host name, you can set your domain name, you can mess around with that, and no one else will see that. Again, a quite specific and particular namespace. Something that might be more interesting is the IPC namespace, or from my point of view. You might think the domain name thing is more interesting, but I think this is cooler. So, the IPC namespace isolates in-kernel IPC mechanisms, which there are two of. The POSIX message queues and systemv IPC mechanism. If you're using other IPC mechanisms, if you're using dbus, if you're using gRPC, whatever to do IPC, that's not affected at all. This is only isolating POSIX message queues and sysv IPC. And it sets up a whole new, well, basically new stacks for these, a new view, and they can't communicate across the namespaces. So you create it and enter it with clone new IPC. Just like we've done before. And this also enters the new IPC namespace. And then you can mess around with, in this case, POSIX message queues as you want to. This one is a lot easier to show. So I have a server. It needs a name. And I have a client that I can send messages from the client to the server, and it prints hello NDC Security, because that's what the client is sending, and then, well, and then it aborts because I messed up something. But that's not that interesting or that important. So what I instead do now is I say unshare -- user -- IPC -- map current user. So now I'm in a new user and IPC namespace. So if I run the same server with the same stuff and I run the same client, they do not talk to each other because they are not separate. But if I then enter the same namespace, what's the PID? 3959. So now I just enter the same user and IPC namespace as the server process. And I can run the client, and suddenly they can talk again. So they are isolated. So for instance, for Docker, if you want to have more processes inside of a container, then they can talk to each other using message queues or sysvipc, and nobody else will see it. Or the host system can do that, and whatever untrusted code you're running in your Docker cannot see it. Okay. Next is the Cgroup namespace, control group namespace. Who here is familiar with Cgroups? Yeah, a few people. Okay, cool. So the Cgroup namespace isolates your view of Cgroups. So what we saw when we did the PID namespace was that you're trying to remove yourself from the system, and you're trying to avoid leaking the information that there are other processes on the system. And one thing that without this would leak is your Cgroup view. If you're mounting your Cgroup file system, then that would leak that there are other processes on the system. So you create it and enter it with clone new Cgroup. And then you can remount the Cgroup, and you will get a new view of the Cgroup. Basically, it will move the root of your Cgroup file system to your, like your process's Cgroup. This is going to be easier when I show you. But the way you do it is you basically add clone new Cgroup, and then you can mount a new Cgroup, and it will look differently. So let's have a look at it. So first I'm just going to run through this without doing anything else. So this is my initial view. I have a mount point, which is sysfs Cgroup, and I'm in this Cgroup, user slice, user 1000 slice, session 2 scope. So if I enter the Cgroup namespace, or no, at this point I've only entered the mount and PID namespace, and you suddenly see that, oh, I'm listing out some PIDs. So this one, this is my PID, because this is a child of a PID namespace. And this is listing out all the PIDs in my Cgroup. And you see there's a lot of zeros here. Those are unknown PIDs to me, PIDs that hasn't been mapped in my Cgroup, or in my PID namespace. So right off the bat, I see that, oh, there's stuff here. There is something that might be interesting in this file system, or in this process. So if I just create a new mount namespace, create a new Cgroup PID namespace, and keep a Cgroup file system, then I'm leaking the fact that there are other processes here. Okay, so let's do that again and do it a bit differently. So I make a new Cgroup. And then I do it like this, because that's easier. There we are, that's easy to see. Then I can echo 14365, which is the PID of the process I created, into sysfs. That looks better. Into the foo Cgroup. And if you're not familiar with Cgroups is like proc, a pseudo file system. When you create a directory there, it creates a lot of files for you. It's not actually reading and writing files, it's telling the kernel where stuff is. So now I put the process on the top here into its own Cgroup. And I see, okay, the current Cgroup now is foo, and I'm PID1. There only exists PID1. But I also see that I'm in a Cgroup called foo, which means there's a parent Cgroup, which is the root Cgroup. I don't want my process to know that, so I create a new Cgroup namespace. But I haven't mounted the Cgroup file system again. So this is running using the old Cgroup file system in a Cgroup namespace. And I see, and a PID namespace, and I see all of these zeros, which are unknown PIDs, which I don't want to know. So if I remount it, now I've created a new root file system. But you see my current Cgroup has changed from /foo to /, meaning my root Cgroup is now / because the Cgroup namespace says that the root Cgroup should be your Cgroup, or the lowest one in your chain. And now I entered a new mount namespace where I rewrote the file system, and now I can remount my Cgroup namespace. I mount it somewhere else for reasons unknown to anyone. And my current Cgroup is /, and when I read the processes in this Cgroup file system, only I exist. So this is removing the possibility for me to know that there are other processes on the system, and also I can now manage my own Cgroup hierarchy. So this is now my Cgroup hierarchy, and I can do whatever I want with it, because I own it. Okay. See how we are on time? Okay, cool. So the last namespace we'll talk about is the network namespace. So this creates a separate network stack. You create and enter it using clone unet. And when you created it, there is a single device or a single interface in that network namespace, and that's the loopback device. Or rather, it's a loopback device. It's your loopback device. Every network namespace has their own loopback device and their own set of interfaces, network interfaces. So a network interface can exist in only one network namespace, but it can be moved between them as long as you have permissions in both. So you can move your physical network interface into a network namespace if you want to. And that means it's available only in that network namespace and unavailable outside of it. You can also create virtual network interfaces and link them and make links between the network namespaces so that you can get a limited access to network, or full network access but your own separate loopback device. Or if you just create it, you're just cut off from the network completely. When I say it creates a new networking stack, it creates its own set of interfaces, its own set of IP addresses, routing tables, IP tables, firewalls, all of that is separate. And when you destroy a network namespace, all the virtual interfaces that you created that is linked to this network namespace is destroyed, and all the physical ones that you moved into this network namespace is moved to the initial network namespace. So you can have physical devices like ETH0 and VLAN and you can move it between these. Or you can make virtual ones and link them together and use IP tables to gain some access, but not that much access and all that. And you can have, and you have different loopback devices. So if you have something in one network namespace listening to a port on the loopback device, and you create a new network namespace, that won't get access to that port. So, like I said, clone new net creates a new network namespace where you have nothing. But that's not really that interesting. So, oh, who am I here? Okay, I'm root. I want to be root, actually. So, if I do this, in my initial network namespace, I have, well, 3 network interfaces. My loopback device, my vWAN device, my 5G network, and VLAN. This is what I have on this device. If I create a new network namespace, I suddenly only have a loopback device. And this loopback device is different from the previous one. But this is kind of useless, because now I just remove this process from the network, which might not be what I want, but it might also be what I want. But you can do stuff to actually get access to it. So 14.872. So IPNetNS attached creates a symlink to this network namespace, so I can access it using the name NS1, which is my choice of name. Then I can add a virtual Ethernet link. So I create a virtual Ethernet pair, where one is named VETH and one is called VETH1. And I can see that they now exist on my device, VETH and VETH1, and they are linked. And I can move one of them into a network namespace. So now I moved VETH1 into that network namespace. And I'll show you the result of that afterwards. And of course nothing, because these are just dead network interfaces. They are down, they have no IP, so let's fix that. So I give it a link local IP. And I can do the same for the network namespace. So in NS1, I set the IP address to 1.2, and then I set the links up. Exec NS1 IP link set VG1 up. So with this NetNS exec, I can run any command I want to inside of this network namespace. So let's try and ping what I set up. So I set up 2 devices. They are linked. One of them, the one in the previous namespace, I gave the IP 169.254.1.1, and the one inside I gave 169.254.1.2. And I can ping each other. They can ping each other, because they exist. And I can also do stuff like set up routes. Because this has its own route. What did I do? Because the network namespace has its own routing table, and I can mess around with that. So if I now list the default route, I see that, well, the one I created is the top one. And since I linked them, it actually got a decent route to the 169.254 subnet. And then on the host, I could use IP tables to route data that comes in on VETH out on the internet or to whatever I want. So at this point, you can do basically whatever, and you can use this to completely limit what is accessible for this namespace. And you can forward ports from your host to inside of this namespace, which is what happens when you do forwarding ports in Docker, for instance. Then that's a IP tables rule. So to show that it's actually had an effect here, when I list the interfaces again, I see I have a VETH1 network interface. And I can also delete that one. And now you see I have no more virtual Ethernet devices, because VETH1 was inside of the network namespace that I just deleted, and so it's gone. Okay. That's all I had for you today. Any questions? Yes?
Could you elaborate on why some distributions like Debian and Arch put a patch into their kernels to disable unprivileged user namespace?
Yeah, so the question is if I can elaborate on why some distros have basically disabled the user namespaces. Unprivileged user namespace. I know there has been security issues with the user namespaces, unprivileged user namespaces, where they suddenly get more privileges in areas they shouldn't. I'm not aware of any such shortcomings at the moment, but of course it's a beast. Like the user namespace is, it sounds pretty simple because you're like mapping users and you're owning namespaces, but security-wise inside of the kernel, it's probably the most complicated because it governs privileges, and it has privileges that only applies in certain scenarios. So it's probably a beast in the kernel compared to what we see. So I don't really know why they still have it disabled, because it's very useful. And I know that stuff like Chromium is using it heavily. It's I'm not really sure why they still have it disabled. I would like to see it enabled because it's very useful.
It's enabled by default, but for example on Arch you may want to install security hardened kernel where it will be disabled.
Okay. Yeah, so the comment here was that it is on by default, but if you add a security hardened kernel, that turns it off. Yeah, and I would guess without knowing that it's because they're afraid of unknown issues that's still inside of it. But I know there has been, a lot of people are skeptical of the unprivileged user namespaces because it has had issues in the past. And it's probably had quite a lot of issues because it's complex and it's very sensitive security-wise. Yeah. Other questions? Okay then. Yeah, in the back.
Where would you use this apart from Docker and other container?
So yeah, so Docker is a big Docker uses all of these because it needs to. And some of them, like I said, are also very specific to, well, containers, not Dockers, but very specific to that use case. But this is also used a lot by sandboxes. So sandboxes, on the Chromium sandbox, use the user and PID and network namespace at least. They don't use the mount namespace because they remove themselves completely from the file system. But sandbox technologies, it's very convenient for. Also, like using this to get rid of or don't have access to the host IPC mechanisms, for instance. But like I mentioned briefly, I've also added support for at least some of that in our unit testing framework because sometimes it's very convenient to be able to test like how do you behave on the file system, and also you could use this to create errors for the file system, right? Stuff like that, which is very convenient with the mount namespace, and kind of have to do overloading of library paths or overloading of the glibc functions if you want to do that without namespaces. But again, it makes it very Linux specific if you do that. So it's a
Network namespaces are quite useful for testing as well. For
Yeah.
networking stuff.
That's true. Especially if you want to do, the comment was that network namespace is also very convenient for testing. And the patch I added to our unit testing framework also does that. I don't think we have anything that actually uses the fact that that's in a network namespace, but to get your own loopback device and being able to do stuff on that or create your own network interfaces.
Hierarchy.
Yeah, you can make whatever you want. But yeah. Yes?
Would you recommend using this for more novice user, or would you say like, oh, use this with great cautious? Because there are so many pitfalls and little things that you have to know before you can actually like make sure that you're doing the right thing.
Yeah, so the question was, do you recommend using this for novice users, or do you need a better grasp of it, basically, to actually use it? To use this for security critical stuff in your production environment or on a production, like in production code, you should have a good grasp of what's going on and what pitfalls might come. I would be very skeptical if we had a new hire starting making patches using namespaces or, well, any of the security features in Linux. Because there are pitfalls, there are stuff you don't know about probably, and you should have a good grasp of it. But for like playing with it, testing it out, trying it out with like unit testing and stuff like that, that's how I started learning with it, and that's pretty convenient. And also like doing talks and having to write shitty code to learn stuff about it, that's a great way of learning it. But yeah, production code, like trying to use this to protect security sensitive stuff without having played around with it and stumble upon issues, I would be very skeptical about. Other questions? Okay, thank you. Enjoy the conference.